All right. So on not Friday, Wednesday, we left off talking about hybridization and how carbon is able to make its 4 bonds. We talked about that, and we talked about the fact that carbon has 3 different hybridization states: sp3, sp2, and sp. And I think we left off dealing with the sp3 hybridization. Is that right? Did we leave off talking about that?
Yes.
So we talked about the sp3 being a combination of the. So let me back up some. The orbitals that are in question are in the second energy level. So when we talk about hybridization, it's only happening in the valence shell, so the highest energy shell. We talked about what valence means and where the valence electrons are, so on and so forth. So with that being said, the sp3 is a combination of all 4 shells in that second energy level. So the 2s and all 3 2p's, you add them together and you get 4, I'm sorry, I keep saying 3. You get 4 hybrids that are what we call sp3 hybrids. And again, the 3 in sp3 only simply means that all 3 p's are involved in the formation of those hybrid orbitals. All right. So we have, if you notice in the sp3 orbitals, there are 4 orbitals and each one has 1 electron, because up here we took those 2 electrons that were in 2s and we redistributed those electrons across all 4 orbitals, so everything got 4 electrons. And that's how a carbon is able to make an sp3 carbon is able to make those 4 single bonds. All right, questions about that? Any questions about that? So now we're going to turn our attention to the sp2 hybrid, and let's look at that. So we're going to take the same set of orbitals. So we're going to say 1s, 2s, and we're going to put those here, and then 2px, and then 2py, and then 2pz, and each one of these has 1, none, and 2pz. So if I took the 2s, 2px, and 2py, that's 3 of the 4 orbitals in the second energy level. If I did that, how many hybrids should I get? Anybody?
3.
3, right? If I take 3 atomic orbitals and add them together, I should get 3 hybrids. So what's going to happen here, I'm going to have to switch over to a new document, is this is going to become, you're going to get 3 sp2 hybrids. Each with 1 electron. And then this p orbital down here stays what we call unhybridized. Right, we're gonna leave it unhybridized. So if that's the case, I'm gonna write it here, and it's still p, and also has an electron in it. All right. So somebody asked a question about hybrid overlap and single bonds, and then somebody asked a question about how do we make double bonds, what's overlapping when we make a double bond. So let me save this, and I'm going to open up a new document because I need more room to discuss this part. Because I don't think I can add a page on here. All right, that's okay. And I'll combine the documents when I post the annotation. Come on. Okay, here we go. Okay, so we said that for SP2, this was all right. So we have 3 hybridized orbitals, and then 1 unhybridized p orbital. Right. So all in each one of these has 1 electron. Right. So for a carbon that's sp2 hybridized, it's going to look like this, right? So you're going to have a hybrid here. You're going to have a hybrid here. And then you're also going to have one here, right? In the shape of a triangle. So you can see here, it's like a triangle. Those are my 3 hybrids. And then you're going to have an unhybrid, that last p orbital, which is unhybridized, is going to be here, right? On the top and bottom face. So this is an example of an sp2 carbon, right? You have 3 hybrids that are flat trigonal around it, and then you have a p orbital perpendicular to everything, right? So if this was to overlap with another carbon that's sp2, let me just show that. All right, we'll go here like that. Here's the carbon. We have another hybrid here and another one here, right? And then we have that unhybridized p orbital here, like that, right? So the overlap here, this overlap where you have 2 hybrids overlapping, that's going to be a sigma bond. Right, so this is a sigma bond, right? Or a single bond, like we call it a single bond, but we can also call it a sigma bond. Right here, when these 2 overlap, the 2 unhybridized p orbitals overlap, and they're going to overlap on the top and the bottom. That is what we call a pi bond. So if you have 2 unhybridized p orbitals overlapping, you get a pi bond. So you should write that down.
Can you repeat the definition of pi bond?
Yeah, I'm going to write it out as well. But a pi bond is when you have it occurs when you have the overlap of unhybridized p orbitals, right? And if you remember, we said up here that if a carbon is sp2 hybridized, you have 3 sp2 hybrids. That's where your sigma bonds are going to come from. And then an unhybridized p orbital, which is able to make your pi bond. So let me show you here. So you have, so a pi bond is unhybridized p orbital overlap. That's what it results from. Right, so whenever unhybridized p orbitals overlap, you get a pi bond. So an example would be a carbon that looks like this, right? So you can see the 3 sigma bonds. These are all of your sigma bonds are the result of hybrid overlap, right? So that's hybrid. All those sigma bonds are going to come from hybrid overlap. All right. And then if you have each one of these carbons only has 3 bonds to it. So the 4th bond is going to be a pi bond. We're going to just write that in here like that. Right. So you have a pi bond and a sigma bond. So anytime you have a double bond, it's the combination of a pi and a sigma bond.
Is that always?
Yes. Every double bond is made up of a pi, 1 pi, and 1 sigma. 1 pi plus erase that. 1 pi plus 1 sigma. That's how you make double bonds, right? So let me go back to the Paxlovid that we were looking at. Let me save this first, so I'm gonna have to come back to it. I apologize for the crudeness of this presentation, but I didn't realize my iPad battery was almost dead. That's all right. We're still gonna make it work. So if we go back to Paxlovid, right here. Right? All of these that carbon right there, let's look at that. That carbon is sp2. If you notice the shape, you can see immediately that it's in the shape of a triangle. You see that? So every sp2 carbon is going to be trigonal and it's going to have a 120-degree angle, bond angle. Right? And the other part that makes it very easy to pick out whether a carbon is sp2 or not is here. How many, if you look at that carbon right here, let me highlight that. If you look at this carbon, how many things are attached to it? Not how many bonds it has, how many groups are around it? 3 groups, good. So you have this group right here, the oxygen right here, and then the nitrogen right here. Is that right? So every sp2 carbon is going to have these characteristics. It's going to have It's going to be trigonal. It's going to have a 120-degree bond angle, and it's going to have 3 groups attached to it. Right? That's not that. Those are all the other characteristics in addition to the double bond that's present. So sp2 carbon is going to have 1 double bond to it, or sp2 hybridized atom is going to have 1 double bond to it. All right, questions about that? So let's look at another group on here, because I want to point out that it doesn't have to be carbon. That's sp2, right? That oxygen, when you took general chemistry, you learned about Lewis structures and John Lewis structures. If we have a oxygen that's neutral like that, what am I missing on this structure? What can I show on the oxygen that's not shown right now? Anybody?
The lone pairs,
Lone pairs. Who was that?
Rake and Bruce.
Nice work. Nice work. Lone pairs. All right. When we draw lone pairs in, normally we just draw them, right? Flat in 2D. But in reality, the lone pairs are actually sitting in orbitals. Right? So that oxygen right there, the lone pairs count as a group, right? And so when we look at the oxygen, it has 2 lone pairs and a carbon to it, bonded to it. And it also has a double bond. So that oxygen is also sp2. Are y'all following that? So the oxygen is also sp2 because it follows the criteria. It's trigonal. It has a 120-degree bond angle, and it has 3 groups attached to it because the lone pairs count as a group. Right? Questions about that? So that's when we think of, let's go through and see if we can find other sp2 hybridized atoms. Help me out. Somebody help me find the next one.
What about carbon? The one where it's double bonded to the oxygen by the NH.
Right here? Uh-oh, sorry. Right here?
Yeah.
Yeah, excellent. That's also sp2, good. Do we have any more?
What about the one in the top right?
Right here?
Where it's, yes, that's the one.
What are you
But
talking
I was
about?
also talking about, yes, I was talking about that one.
You're exactly right. That's excellent. Excellent work. This is this carbon is sp2 as well. Right? And so is this one. Not 2ps. Come on, Russell. Sorry. sp2. Are we following? Everybody okay with that? So
I follow with the oxygens. Do we just assume that any oxygen that's double bonded is a loner pair at the end?
Oh yeah. Okay, so with oxygen, that's a great question. It opens up the door to another part of our discussion. So when you have a atom like oxygen, right? If it has 2 bonds to it, it's gonna by default have 2 lone pairs just based on the valence electrons around it. It's got 6 valence electrons, right? If it has 1 bond to it, then it's gonna have 3 lone pairs and a negative charge. If it has 3 bonds to it, which it can be hypervalent. It's got 1 lone pair and it's positive. Right, what I want you to notice is each one of these has a specific hybridization state. So here, this is going to be sp3. You can see that the 2 lone pairs are a group, and then you have 2 single bonds or 2 sigma bonds to it. So that's 4 groups around that oxygen. So it's sp3. Here it's also going to be sp3. because it has 3 lone pairs. That counts as 3 groups and 1 sigma bond. So it's got 4 groups around it. So it's sp3. And then this also is sp3, right? It's got 4 groups around it. And if now when you see it doubly bound to carbon or some other atom, then yes, it is always going to be sp2 because it has a sigma bond and a pi bond to it. Are we following? Are we okay with that?
Yes.
All right. Okay. Now let's talk about sp hybridization. All right, let's talk about that. Because sp3 we talked about 4 groups, 109.5 bond angle, 4 sigma bonds, no double bonds, all single bonds. sp2 is 3 groups. It is 120 degrees for your bond angle. It is 3 sigma bonds and 1 pi bond. Now we need to talk about sp hybridization. All right, so let me go back to, I'm gonna save this. Let me go back to the other sheet we were on, not that. Okay, and now we're gonna talk about sp hybridization. We talked about sp2. I need to be able to add a page to this. This is really frustrating. You know what? I'll just make another document. How about that? I'll just make it a PDF. I'm going to combine all this so that it'll be coherent when I post it to Blackboard. Okay, so now we're going to talk about sp hybridization. All right. If we think about sp3 and sp2, what do we have to do to make the sp3 hybridized carbon? What do we do? We took, and I'm just going to write this, 1s2, 2s with 2 electrons, and then 2px, 2py, and then 2pz, right? And it's 1, 1, and none. Is that right? So when we did sp3, what do we add together to make the sp3 hybrids?
The S and the 3 P's.
S and all in the second energy level, right? So we added all 4 atomic orbitals and we got 4 hybrid orbitals. For sp2, what do we do to make a sp2 hybridized carbon? We have one of the S's in the second energy level and then 2 of the P's to make 3 sp2 hybrids. Is that right?
Yes.
All right. Okay, good. So now with the sp, what do you think? Just think about this, a logical progression from sp3, where you add everything together in that second energy level, to sp2, where you only add some of the orbitals together, 3 of them to be exact, in the second energy level. sp means what? I'm only going to take, and again, this is a way to explain what we see. This is a way to explain the fact that carbon can be present and have 4 single bonds to it, or it can be present and have 3 sigma bonds and a pi bond to it, or it can be present and have 2 pi bonds and 2 sigma bonds, always meeting the octet rule by having 4 bonds to it, but not necessarily always in the same manner. All right. So here we're just going to take those 2, the 2s and 2p, we're going to add them together. So I'm taking 2 atomic orbitals, I'm going to add them together, and it's going to give me 2 hybrids. Right, so S plus P is going to give me SP plus SP, because if I take two atomic orbitals, I get two hybrids. So S and P together are going to give me two SP hybrids. Are y'all following that? So it's going to be SP, SP. What about the other P's that didn't get touched? Think back to SP2. What do we do with that P? Did we throw it away?
Stay unhybridized.
It just remained excellent, unhybridized. So here, I'm gonna redistribute the electrons, which I have to do here, right? 4 orbitals still, two hybridized, and 2 unhybridized, right? Untouched. What do you think? Now let's think logically about what we've done so far. What do you think about the 2 unhybridized p orbitals? What happens when you overlap unhybridized p orbitals? What kind of bond?
bond?
Pi bond. Excellent. What happens when you overlap hybrid orbitals?
A sigma bond.
So when you look at this configuration, you got 2 hybrids and 2 unhybridized orbitals. What do you think this atom is going to look like? Like, how's it going to fulfill those 4 bonds that it's making? Think about it. You got 2 hybrids, so how many sigma bonds am I going to make on a carbon like this? 2, right? Let me write it out. So here's what the carbon looks like. It's got a hybrid go in this direction, one go in that direction, right? So that's my hybrid orbital. And then I have 2 unhybridized p orbitals. One is going to be perpendicular here. Keep in mind the hybrids, remember, I don't know if you could tell, but you have a larger lobe here and a smaller lobe here, right? So that's the hybrid for each one. And then the same thing here. So the P, unhybridized P, is the same, both lobes are the same size. So I got one pointing vertical, perpendicular, and I'm going to have another one here, like this, coming out of the page, pointed at us. That's the other P, right? So when this overlaps with another carbon like it, or another atom like it, it's going to make a stick bond here, right? It can make a sigma bond on the backside too with something. That's also going to be sigma. Same thing over here. That's going to be sigma to some other atom. And then the unhybridized orbitals are going to overlap here. Get this. Right? And then by the same token, the other p orbitals that are here perpendicular to the ones in green, they're also going to overlap. So we're going to have some overlap here and here. Right, so in the end, this sp hybridized carbon, if it's bonded to another atom that's sp hybridized, it's going to look like a cylinder. Kind of like that, right? So it's going to be linear. It's going to have a bond angle of 180. Right? It's going to have 2 groups attached. But it's going to have 2 sigmas and 2 pi bonds. That's how it fills up those. It's 4 bonds, 2 sigmas and 2 pi's. All right. Questions about that? If you watched the video, the hybridization video, you've seen this already. This is just kind of reviewing that. Right? Questions about that? Right? Let me go back to the example, Paxlovid, and let's look and see if we can find all the SP hybridized stuff in here. Are there any SP hybridized carbons in here? If you can point it out,
It's the one that's triple bonded to the nitrogen.
this one right here. Excellent. Who was that?
Kadir.
Oh, great. Excellent. All right. Right here. This carbon, I need to edit this. This carbon right here is SP hybridized, right? Now let's look at the characteristics. You can see that it's linear, right? The angle is 180. You can also see that it has two things attached to it. It's got this carbon up here, and it has the nitrogen down here. So it's got two groups attached. It has a triple bond to it, and that if a double is made up of a sigma and a pi, right? We said that earlier. A triple bond is made up of a sigma and two pi's, right? So anytime you see a triple bond, that triple bond contains two pi bonds and one sigma bond. All right, we following? Yes, no?
Yes.
All right. So triple bond is one sigma and two pi's. And then you have, so you got a triple bond to it, but it still has its four bonds because it's bonded to that other carbon on the backside. And it's 180 and it's got two groups attached. But the easiest way to spot whether or not an atom is sp hybridized is to look for a triple bond. Same with the sp2. If it has a double bond to it, then more than likely the atoms that are in that double bond are sp2 hybridized. If it has all single bonds, more than likely those atoms are sp3 hybridized. All right. Questions? Any questions about anything? And again, I apologize for how this is all scrunched together, but yeah, never mind. The iPad it is what it is. But we'll have that together on Friday. All right. Any questions about anything? All right. Let me do this. I'm going to switch over to my laptop and I'm going to pull up this the first one of the handouts from first module, and we're going to kind of walk through. I'm not going to be able to annotate it, but we can walk through it and you can annotate on your end. All right. So let me switch over to my laptop. The sound. Actually, I'll keep the sound going on my phone and disconnect the sound on my laptop.
We can't hear you.
What about now? Sorry.
Yeah.
Okay, so with the, let me go back because I thought my other device was still going. All right, so every module has a summary, learning objectives up top. If you don't get the email that I send out with the videos to watch for class, you can always come in inside the module, and where it says watch, all the videos are going to be here, right? And then the discussion board, you can do that anytime between the time you start the module and the time that we take the exam. Most of the exams are going to include 2 modules. So so the discussion board can be done anytime between the time we start and the time that we take the test. The pre-assessment is the first thing you ought to do in every module. You click it, you just take it. Don't worry about studying for it. Don't worry about what you get wrong. It's just a pre-assessment to see how much of this information you already know. The reading is the same as the learning objectives. It just tells you what section in the book. And again, this is based on the 3rd edition. Lectures are the same as what to watch. So you don't really, there's nothing new here. Supplementary resources, there may be a handout or 2 that is not necessarily to be turned in, but just to help with what we're doing. And then here where it says assignments, that's where all the work is going to be. So I'm going to pull this one, because I think we can answer some of these questions now, especially here.
Excuse me, Dr. Russell. Will we print this out, or will we like
It's
use
totally
like
up to you. If you want to print it and write on it and then scan it back in, that's fine. If you want to download it and write on it electronically using your device, that's fine too.
all right.
It's however you choose to do it. All right, let's go to, let's see. We'll come back to this. We'll start doing this on Wednesday. But let's go to here since we're talking about hybridization. Here, we can do this. Let's look at 1.70. All right, it says what orbitals are used to form each indicated bond. For multiple bonds indicate the orbitals used in individual bonds. So we're looking at, let's start here. All right, let me zoom in on that. Let's start right here. So you have a carbon bonded to another carbon. What's the hybridization state of each of those carbons? And how can you tell? Keep in mind, every vertex, if there's no other atoms there, it has 2 hydrogens on it. So what's the hybridization state of these 2 carbons?
SP3.
Both of them are sp3. That's exactly right. Excellent. So what orbitals had to overlap to make this sigma bond right here between these 2 carbons? That's what this question is asking. If it's sp3, that means all 4 of the orbitals around that carbon, all 4 of the hybrids are sp3 hybrids. So when I take these 2 carbons and bring them close enough together to make a covalent bond and share a pair of electrons between them, what orbitals overlapped?
Hybridizing.
And what's the hybridization state again?
SP3.
So with this example, with these 2 carbons, you have overlapped 2 sp3 orbitals to make that bond. So we would say here that this sigma bond is a result of sp3 overlap. Right? It's sp3 overlap. Yes.
So
No.
to answer this question, like
Mhm.
to put it on paper, we would put sp3 plus sp3 and we'd be done.
Yeah. Or not plus, just put a dash in between the 2. So sp3 dash sp3, and that's telling you that the orbitals used to make this bond are sp3 hybrids. All right, what about here? This is kind of tricky. We know that this carbon is sp3, and we'll stop here, and we're gonna pick this up on Wednesday. We'll dive in on Wednesday. I think we got enough information now where we can dive in and start plowing through this handout. All right, what about here? we know that this carbon is sp3. What is hydrogen? I'll buy lunch for the first person who tells me what orbitals make up hydrogen. Anybody? Going once. Going twice.
When you say orbitals, you're talking about the SP, correct?
Think about
So-
okay, so let's go back to general chemistry. What's the electron configuration for hydrogen? What's the atomic number for it? Anybody remember that?
One.
One.
Okay, I heard somebody
it
out of the
sigma?
band of voices say 1s1. Who was that?
Michael.
Michael. Good. So if the hydrogen is 1s and then the carbon is sp3, what's the overlap? How do we make that CH bond? Because you can't hybridize hydrogen because it only has one orbital, the 1s orbital. So that's
Is
no
it just
hybridization.
SP?
Say that again.
Is it just SP?
No, it's not. It's not sp because that sp is an actual hybridization state of carbon, but it is sp3 for the carbon and then s for the hydrogen. So that's what's overlapping there, the sp3s orbitals. Right. I think I said this back when we first started, that the only way you can make a bond is from orbitals overlapping. Is that right? Did we say that?
Yes.
Yeah.
So the SP2?
No, it's not. It's sp. The carbon right here is sp3. The hydrogen is s. And so when they overlap, the orbitals that are overlapping, you have one sp3 orbital from carbon overlapping with the s orbital from hydrogen. So it's sp3s overlap. Does that answer your question? All right, we're going to hit this hard on Wednesday. So if you don't already have this downloaded, go ahead and download it. And we're going to hit it pretty hard on Wednesday. And introduce some of those other topics like polarity, polar covalent bonds, dipoles, all that type of stuff. All right. I'm over time. I apologize, but are we good?
Yes.
Yes.
All right. We'll see you on Wednesday. Hopefully you'll have time to get to your next class. I apologize for that. And get this handout from Blackboard if you don't have it already.